So this is the plan for today. We prepared the tutorial, so we split it in two parts. The first part is going to last about an hour, in which we will introduce the basic concept of self-calibration and including a leaf demo by Emily. After that, we're going to have a short break, a short coffee break. During that time, we will let you do some exercise, and we'll be online to discuss what your. And after the break, Anita Richards will take the floor to discuss advanced topics on self-calibration. And I want to say that we are in this online mode, but we remain available after the session for one-to-one discussions. If someone encounters any issues when running the script or something that remains unclear, all of us will be available in the afternoon for another Zoom meeting one-to-one or at another convenient time. So you can contact us in the chat or by email afterwards. I would like to ask you to download the latest script for the training. And we also include an advanced script that does self-calibration on the line. We will not discuss it, but we make it available for you to take a look and also come back with questions to us about this advanced script. And at any point of Emily's leaf demonstration, if you cannot finish the imaging loops because your laptop is too slow or because you just cannot, you can grab the tar file caltables.tar.gz that is in the folder that pointed out, and then just put the corresponding calibration table in your working folder, and then you can continue with the plus tips and further imaging, etc. And for the rest, yeah, I will give the floor to Andres to start the presentation. Thanks.
Thank you very much, Carmen, for the presentation. Thank you for the invitation to participate and contribute in this tutorial. My name is Andres Perez Sanchez. I work in Allegro. This is the ALMA ARC node for the Netherlands. And today we are going to talk about self-calibration. So before getting into self-calibration, let's remember that every telescope that observes and produces science for data, high quality data for science, they always will observe the science target in between observations of many calibrators. So in the y-axis in this figure, you can see all the names of those calibration intents that ALMA does when a standard program is executed. So you can see also along the x-axis the timeline of the observation of this program in particular, and you can see that the amplitude and the bandpass calibrators are observed before the phase and the science target. And you can see also that the phase and the science target are observed in this kind of a sequence that is a loop that starts and finishes with observations of the phase calibrator. That shows how important the phase calibrator is for all the corrections that the data needs before being released to the PIs. So the phase calibrator normally is a bright source, compact source, and it helps you to characterize the atmospheric fluctuations that affect the transmission of the incoming signal, that along the line of sight to the phase reference. So that is one of the reasons why you always want to have the phase reference very close to the science target for your program. Sometimes that is not possible, and you end up having observations of your phase reference not as close as you might want to your science target. In those cases, when you apply the corrections that you find on the phase reference to the science target visibilities, you might end up not fully correcting and having some phase residual offsets that will make lower the quality of the final product that you want to put in the paper, that very map that you want to make. Those phase offsets can be corrected, yes, provided that the science target is bright enough. If that is the case, then you can use the science target to calibrate those phase fluctuations along the line of sight. If that happens, then you are doing self-calibration. You are using the science target visibilities in order to calibrate the science target visibilities. At the end, you end up using a subset of the science target visibilities to calibrate the rest of the target visibilities. So that is self-calibration, using the science target to calibrate the visibilities of the science target. Okay. In the figure in this slide, we can see three maps of the same target. From top to bottom, we can see the map that is created after the calibration using the phase calibrator that was observed for this program. You can see that the image is kind of not good. The noise is dominated by negatives, and if something, it looks more like a residual map than to a properly clean map. In the second panel, you can see the same source after one run of self-calibration. This one is done only on phases. That will be clear at the end. This one, self-calibration, is done only on phases, and you can see that you can recover more flux from the source. Still, some room for improvement. You can see that there are some symmetric noise features that for sure they are not real, and you can find some room for more improvement. And that is the case for the last panel in this figure. You can see that the source is better described, and this is actually after the final step of self-calibration, that is also self-calibrating the amplitudes and together with the phases of the source. Okay, so the final goal of self-calibration is improving the quality of the final product, that of that final map that you want to include in your paper. Self-calibration is a shorter version of the entire process of calibration that interferometric data requires. So if we are doing self-calibration with CASA, there are 4 tasks that we are going to use: Tclean, FT, gain cal, and apply cal. The last one is another Tclean. Before starting self-calibration, you should select a subset of the visibilities of your science target that you are going to use as a new calibrator. With Tclean, then, when you run for the first time Tclean, you will create the first figure, the first map, and also a model. Then, when you run gain cal, you are going to compare the model and the visibilities, and you are going to find the interval of time in which the model and the visibilities match the best. Gain cal will result then in a table that it contains all the correction parameters that were found in order to make that match possible, and it will apply it on the fly to the visibilities that we started cleaning at the beginning. When you clean that again, the output will be a much better image, higher signal to noise, and a new model that you can use again to restart the process. So self-calibration is an iterative process that will finish once, for example, you can check that the signal to noise in the final map is not getting better, and that is a clear sign that you should stop working with self-calibration, that not more improvement can be found. So signal to noise is an important parameter on this. You can already see that. And actually, signal to noise is the first thing that you should look at when deciding if you want to do or not self-calibration. If you have ALMA data, and that ALMA data was observed with more than 40 antennas, then the signal to noise, the minimum signal to noise that you should have in the initial map is a few hundreds. If you get to work with ALMA data that was observed with less antennas, then the signal to noise you can use a few tens of, for signal to noise, and that will work. That is the case of the data sample that we are going to work today. It was observed in 2013 with 20 antennas, and the science target was BYCMA. It was observed in band 7. BYCMA is a strong continuum source, and it was observed in band 7 using two spectral windows, spectral window 0, spectral window 1, and you can see that in spectral window 0 there is the detection of the water maser line at 325 GHz. That is the frequency of the transition. But in the continuum, in the baseline of the spectra, you can see that there is also detection of thermal lines. Spectral window 1 also have detection of thermal lines, and these molecular lines are coming from all the material that BYCMA, a red supergiant, is gradually losing, and this material get cold, form dust molecules that will get to form the stellar wind, and that is what we are detecting here. However, today in the tutorial we are going to work only with continuum. We are going to do the continuum self-calibration. Why this dataset needs some self-calibration? This was taken in 2013 in science verification times in order to test long baselines. Long baselines are a challenge actually when you want to calibrate the phases, and that is already a good reason why we want to try self-calibration with this dataset. For that, I will leave the floor to Emily, and she's going to start working and showing how it's done. Thank you very much for the attention, and yeah, I will stop sharing here.
Okay, hello everyone. My name is Emily Moravik, and I'm associated with the Czech node. So a major part of this tutorial was to have a live demo. So I will be leading this demo to take us through the first round of self-calibration. So first, we need to open up CASA. This can be different depending on your alias setup. So for me, it's simply CASA. Let's bring up Windows. Just going to fit this so I can see everything. Okay, excellent. So off we go. So we have created a script for this tutorial that is called the iTrain self-cal, and it's organized into various steps that have the individual commands to be executed. And we'll do this by setting the variable called mysteps and then execute that file. So for example, this was mysteps 0 and 1. So the script will set a lot of important variables just automatically for you. And we asked that you executed steps 0 and 1 before the tutorial. However, if you have not done that, please do so now, as it will do some diagnostic plots and also create a dirty image for you. I'll go through a few of these things that those steps created. So as Andres explained, we have two spectral windows which have some molecular lines in the maser line, which you can see here, and those will be PNGs in your folders there. We also have the list obs, which gives you all of the interesting and important information that you need to know about the observations for this data set. And again, as Andres mentioned, we are going to, for this tutorial, only do the continuum self-calibration. So the cont-chan, which is the continuum channels, is very important that that is included in all of the commands which we have done for you, but your results will be different if you're including the lines as well. So it's important to, before you begin self-cal, to know a bit about your target and about the structure. So we've included the creation of a dirty image, which you can see on the left for you. It's also good to do a test clean just to see what the structure of your source is before you do self-calibration. So that is shown here on the right. So I'm going to be taking you through one round of self-calibration. As Andres explained, there's a certain progression. So we'll first use Tclean to produce a model, and then we will save that model to our measurement set using FT. And then we will choose a solution interval and create the solution table using GainCal. So GainCal will compare the model to the data and produce solution tables. And then this tutorial, we will be investigating solution intervals. However, when you do this for your own data, it's best to do this first, to look at the solution intervals and investigate to choose that the best solution interval. And then we will apply the calibration table that we choose that has the best solutions, which is the product of GainCal. So we are going to do our first conservative Tclean. And this is a very, very important step. And we say conservative because when you do Tclean with the intention of doing self-calibration, you only want to include what you are absolutely certain is real emission. You don't want to include any noise blobs, etc., because you could induce fake features in the self-calibration process. So I'm going to show you what that looks like. Some of the important parameters for Tclean for the self-calibration process is the viz. So that's your measurement set, which spectral windows, deciding on your image size and cell size that you'll be using for your data set, the spectral mode, the spec mode, and also whether or not to save the model. We'll be talking a bit more about these parameters in a bit. So let's go ahead and do our first Tclean. So we set my steps is equal to 2, and then we execute. Okay, go. So it's just starting up here, and a window will pop up where we can start creating our conservative mask. I will mention too that, so I'm using a computer that has 12 cores. If you're doing this on a laptop, your process of Tclean may not go as quickly. And if you fall behind, and this is the case, I would recommend just doing maybe 1 or 2 rounds of Tclean, and just do that so that you have a model of some kind, and then you can play with having a deeper clean later in the process. Okay, so here is our first iteration. So as I mentioned, we want to have the emission in the model that is really real. So we're going to zoom in on here. Okay, so we want to include really the brightest emission. So we're going to create mask. So I chose the parameter or the button that lets you define the shape of your mask. So we're going to simply include just the pink, the brightest emission here. And then you go to the next iteration by using the arrow here. So here we go. So the goal is to get to a point where the emission, the peak of the emission in the mask is similar to the peaks in the noise outside of the mask. So we will keep going until about that time. Again, if your computer isn't going as quickly as mine, just do maybe 1 or 2 rounds and then stop there. Okay, so here's our second round. All right, so we have some more pink, so we're going to go ahead and include that. Just include most of this. Right. So we'll end up doing this probably 3 or 4 more times until we get include most of the components that we want to inside the mask and have those included in the model. Right, here's our next one. As you see, we're starting to see more structure and more emissions. So we're going to again expand. So I'm going to just expand this a little bit. Right. So we set the number of iterations to about 200. Just because I've done this a few times, I know that we'll get to about 150. As you see, we've already done about 15 iterations. Okay, and we're starting to see some extended structure. This looks pretty good. We're going to go ahead and not edit the mask for now and just let it go. We'll include all of this in another iteration or two. So again, we're being conservative, very conservative. You know, one might have instead, when you're doing a test clean, you know, included all of this in the mask, but we're trying to be conservative. You're trying to include what you are really certain is emission. Now you'll notice our noise blobs are starting to become more noticeable on the outskirts, but we're going to forge ahead. Include most of this. Right. Yeah, so these conservative cleans might feel quite different to what you might be used to if you haven't done self-calibration before, that it's very tight. Okay, we're starting to get there. So again, these noise blobs are starting to pop up, but we still have a decent amount of extended emission. I don't need to zoom in. I can see that we have included the relevant bits and pieces. So we'll go again. Now we did use the save model equals true parameter in Tclean, which should allow the model to save in the measurement set. However, we found that that doesn't always work. Okay, so we're getting to this point here where the noise here is actually higher than what is here in the center. So there's a couple of different options. So we'll stop here. You can either stop completely and the model won't save, or you can change this iterations to 1 and hit this button that allows it to continue on. So we will just stop for now. So I'm going to tell it to stop here. Okay, so now we theoretically have our model. And as you can see, we stopped when the emission inside of the mask is similar to that in the noise blobs. And we want to look at the initial image statistics. So we have a function defined in the script for you in this next step or in the first step that produced these statistics. So you can see that here in that. So this is the image that it created for our first round. And here is the area over which the statistics were calculated. And so we did about 150 iterations, and we have a signal to noise ratio of about 51. However, if you're doing this, for another object, you won't have this predefined mask. So you can define that yourself, or a quick way to do this is using the viewer to look at your image and create a box and look at the statistics. You can find the peak within the area of emission, and then you also can find an area that's free of any emission or artifacts, to find the RMS. And then you have your signal to noise with your peak to our RMS to get the signal to noise. Okay, I wanted to show you what the model looks like. Which components do we include in the model? So you can actually see here the various components that were included. So we definitely included that which we're pretty sure is actually real, and we didn't include any other noise blobs. Okay, so now we are going to save the model. So we go to my steps equals 3. I'm going to execute that while I'm talking here. Okay, so it's very, very crucial and important that you check that the model has been saved for the self-calibration process. And you do that by using plot MS. And if you see that this that the model is all at 1 Jansky, that is the default, and it means that the model has not saved. And this is the case for our situation. So there's a couple different ways that you can try to and truly enforce the model to save. You can put the save model equals true in Tclean. This sometimes works, sometimes doesn't. So you always need to check. FT is that it does force the model to save. During interactive, you can set that the final number of iterations to 1 and press the button that lets it continue on through the end, through all the iterations that you have specified. So that would be 1. You can also run Tclean again without being interactive and set it the n iter to 0 or 1. But we have found that FT is the safest and quickest way to do this to ensure that your model has saved. So what our step is doing currently is making those plots for you and then using FT to save the model. And then we plot it again after we've executed the FT task. And we see that now the model has structure in the with amplitude and UV wave. So you can see that there's the structure and it's no longer equal to 1. And we know that the model has saved. So this step can take a little bit of time. So I'm going to just speak about some of these, the next steps. So we have created a model and saved it in the model column using our step 3. And now it's time to create our solution tables using GainCal. So GainCal calculates the difference between the model and the data column. And it does this in various ways and there are a lot of different parameters that we can put into GainCal. So you have viz, which is the measurement set, the cal table, which is the name of the table that you are creating, the solution interval, which is solent, which is the interval on which you're calculating these solutions on. You need to choose your reference antenna, typically one that is well behaved and is near the center of the array, your spectral windows, and also cal mode, which is the calibration mode. A is for amplitude, P is for phase, and AP is for amplitude and phase. So typically you want to do phase first and then amplitude. So we will be doing phase. Your gain types are whether or not you want to combine based on polarization. So the gain type G is you determine gains for both polarizations. You determine solutions for both. But if you set that to T, it will combine the solutions for both polarizations. You can also set the minimum signal to noise ratio at which you want the tasks to flag data. We'll go into that a bit more. There are various ways you can combine data to get higher signal to noise in your solution tables. So we will go into some of these parameters in more detail later. But while this is still going, doing the saving the model and doing the task FT, I will talk about solution intervals. So something that's very key to self-calibration is a solution interval. So what is a solution interval? It is the time range over which to calculate the gain. So it can range anywhere from int, which is the integration time, which is the shortest interval in which you can calculate the solution, and then infinite, or inf, which is the scan time. So you can calculate your solutions on a level anywhere from int to inf. And so what do you want in a solution interval when we are doing self-calibration? Well, you want to balance two things. You want to balance sampling the variations in the solutions, so capturing the structure of the solutions, while also flagging the least amount of solutions and having high signal to noise in your solutions. So it's a balance between these two things. And we'll talk about this a bit more in the advanced slides. Yes, this step 3 tends to really take a while. So I hope perhaps maybe yours is not taking as long, but I will just keep on explaining solution intervals while we finish up step 3. So here's an image of what solution intervals look like. So I'm going to go ahead and go back to the CASA prompt here and start the my steps equals 4, which is going to create these various solution interval tables, various gain tables with various solution intervals for you to peruse at your leisure. And so there'll be windows popping up here and there while we do this. Okay, so this is a demonstration here of what various solution intervals look like. So the black are solutions on the int, the integration time level. And so this is for both polarizations. And then, okay, so it's going to start popping up here to show you what this looks like. And you can peruse through the various antennas and such. I'm going to go ahead and exit out and show you this through the presentation instead. Okay, so black is a solution interval of 10 seconds or integration, and then the blue is 60 seconds. And then the these individual points that have lines is on inf, or the scan time. So you can see how the blue samples the black, and then these individual points get the overall structure. So these tables that we can view through plot MS, which popped up for you on the solution interval inf. I'm going to be showing on the solution interval int. It's very useful to just get a sense of the data by looking at these tables on the int level, just to see what you're dealing with. So this is for each pair of antennas, etc. So, and then I just wanted to point out your reference antenna is always going to look a little weird. You'll notice that the gain phases are much smaller compared to the others, and also have some interesting odd looking structures. So we can investigate various solution intervals. So I'm just going to go ahead and execute that, and I would encourage you to do so as well, so that we can do that. All right, so this is calculating solution intervals for various, calculating gain tables for various solution intervals. So it's good to investigate factors of 2 times the integration time, or simply doing 1, 2, 3, 4, 5 times the interval time to find the best solution interval. So these are, this is doing this in a loop, and it'll, all the solution tables will be, or the outputs of these will be in this folder phi1 checks. So let's look at some of these. I wanted to show you what the solution intervals actually looks like. So here we have it on int, and then we have 20 seconds. So you can see they're structuring, it's sampling the structure. And then we have at 40 seconds, we have less points, 80 seconds, 160 seconds. So this is increasing in factors of 2 to the n. And then we finally have at the inf level, so the scan time, So that's more of a scalar correction. So that's a demonstration of what the solution interval is and what that looks like. So as I mentioned, you want to have a balance between sampling the variations in the solutions, so capturing this structure, and also flagging the least amount of solutions. So when you have lower integration or lower solution intervals, they'll have lower signal to noise, and you may end up flagging more of the solutions. So for this tutorial, we decided to do inf first, so infinite or the scan time, and then apply a shorter round to capture. So we'll be correcting for more of the scalar differences between the phases, and then applying for more of the structure, correcting for the structure. So something I remember that I was concerned about when I first started doing self-calibration was all of these messages. And so in the terminal, you have seen that as we, so here we did this, we calculated the gain tables for the solution interval of integration time. And you see there are a lot of messages of how many solutions may be flagged that have a signal to noise ratio less than 3. And then we get to 20 seconds, and there's still quite a few. But then you see this dramatic increase between, or decrease of the number of solutions that are flagged, really, or due to lower signal to noise. And you can see at the end here that none of them were. So a sort of rule of thumb that you could use is you don't really need to worry until there are more than 10% flagged. You can also adjust this to your comfort level, and you can also control this on whether or not the solutions are actually flagged using the cal mode parameter and apply cal, which I'll talk about a bit more. But I wanted to explain these messages that you will see in the terminal. So in the script, we have a step 6, which is more for the advanced. So I'm going to skip, and you can execute at your leisure when we do the advanced slides, but it's more of a for you exercise. So the next thing we're going to do is apply the calibration table that we chose. So when you do this, you should go through all of these solution intervals and look at them and decide what you want to apply. So as I said, we're going to apply the solution table that, or the gain table that is using the solution interval of inf, or infinity. So we're going to do my steps equals 7, and we're going to execute that. So while that's happening, so this can take a bit of time. I'll talk about this a bit more. So we applied this gain table that had the sol int is inf. So you have your measurement set, and then the spectral windows that you want to be the solutions to be applied to. The spectral window map is used if you combine any spectral windows or just various things so that you can actually tell it which solutions to map to which windows, which we have a slide on in advanced. And then this apply mode, I'm going to talk about a bit more, but so there's no output of this. It simply applies your gain tables to the data column to get a better corrected data column. Yeah, so let's continue forward. Again, so if you're using a shorter solution interval than inf, you will see these messages again that reflect what we see here from the gain cal task. And it will tell you how many are flagged. And you can actually control whether or not the solutions that have lower signal to noise, you can control whether or not those are flagged. If you use cal flag, it will apply these flags to the data. If you use cal only, it will not apply those flags from the solutions. So again, wouldn't worry. Oh, this should be less than. Yeah, so, or I would start to worry if you're flagging more than 10% of your solutions. Okay, so this is a demonstration of what actually happened visually. You can see what happened. So we applied this gain table. We had our solutions on the INF time scale. And here the red was the data column in the visibilities for one antenna, one spectral window. And then the blue is after the gain table has been applied. So you can see that the effectively the scalar from using the solent of INF has been applied, and the solutions have all been more normalized to one another. So what have we done so far? So we did Tclean to create our model, and we made sure that the model saved in the measurement set using FT. And then we used GainCal to investigate solution intervals and to create a table that has solutions and corrections that were created by comparing the model to the data. And then we chose a table and applied it to the measurement set by using ApplyCal. And now, so self-calibration is a very iterative process. And I've taken you through one iteration, but in order to see the effects that we've had on the image, I'm going to do Tclean once more to create a better image and model. So we're going to do my steps equals 8. Oops. 8. And we're going to execute this. So we're going to do this Tclean once more. Now, I'm going to create a mask again. So we're going to go through this process again. You could use the mask. If you're a more advanced user, you can use the mask from the last clean as a starting point. But we're just going to create the mask again just to drive home that point of having a very conservative clean in the self-calibration process. And this will, we're going to create a new image that shows what happens after we have applied our first table. So, okay, here we go again. Really just including what we know is real. Now this time around, we're a bit more informed about our source. So I could have had a larger mask, but I'm just going to go ahead and do this as we did before. So just let that continue on. So we're going to talk a bit more about how to really choose a good solution interval in a very quantitative way in the advanced slides, because I know that is usually one of the main things when you start out is how do you choose a solution interval? Okay, so now we've got some more structure. So before, again. Just keep it going. All right, next set. Okay, as we know, we have more structure. Just gonna keep doing this. Trying to be conservative and also quick. All right, getting there. I'll just go ahead and, for time's sake, and then do the next one a little bit, and expand the mask a bit more in the next. So we're doing this second round of Tclean to set up the next round of self-calibration to create a better model, and also so that we can see improvement that has been made on the image from our work. Okay, including all of this. Right, so we're almost there. Okay, looks pretty good. One more, I think. You'll notice some of the structure here in the image. I've spoken to scientists who worked with this data set quite a bit, and this could be something called basket weaving, where you have you have a lot of structure in the image due to lack of UV coverage. Okay, looking pretty good. So we're going to do one more. We still have, notice we still have higher peaks inside the mask than outside. So we're going to keep going as we want to reach the point when the noise and the noise outside mask is equal to that what's left inside the mask. Okay. Yeah. So I'll just zoom in a little bit. You know, this is a little different. Looks a little different than it did before. You know, you could still expand this mask a little bit. You know, you wouldn't necessarily. Not sure. I don't know if this is real or not. So I'm not going to include that. And but I'm just going to keep it as it is and do one more. Okay, yes, we have reached our point where we've got a lot of noise and such here in the background. You might be able to do one more or something, but just to be conservative, going to stop. And so we're going to stop here. Okay, and you'll notice that our statistics have popped out here at the end again for you. And you can compare the images. So we have our image from after the first, when we did our first Tclean, before we did a round of self-cal. And now we have our image that we created after this round of self-calibration. So these are scaled to the same, and you can actually kind of even see, it actually might be difficult, but if you look on the slides in your own PDF, you'll see that the noise level is lower. And we have this increase of a factor of 2.5 in the signal to noise. So this, this is a little different, but we have this large increase in the signal to noise. So we have done our job correctly and have increased the dynamic range of our image. And I'll show you this a bit, what the model looks like. So here was what our first model was and our second model. They look pretty similar. If you zoom in on it, you'll see that there are more components along here, higher up here, and just getting some more of the finer detail of the structure of the source, capturing that. And so now I will hand it over to my colleague, Carmen.
Okay, yeah, so now it's your turn actually to do some work. We're gonna take a break in the presentation, and we will give you some time to think about what step would you apply next. So we have given you the tools to explore the next solution interval that could be applied. As Emily and Andres have already explained during the presentation, we give you, like the hints are try to figure out a solution interval that traces the variations in time, but also keeping a good balance with the number of solutions that are being flagged to keep a good signal to noise. So you can use the script that was given, the iTrain self-cal.py, and you can feel free to modify it to try. We suggest that you explore and you compare when you use solint interval int, which is the duration of the integration time, compared to, for example, a 60-second interval. You can modify the step 11 in the script and run it with the solution interval of your choice, and then run step 12 to apply it and make an image with step 13. But you can also feel free to run step 9, which is going to create that loop of all the plots for all the different solution intervals that the same as Emily did for the first loop cycle. And yeah, for the rest, I suggest we take a break, a 15-minute break. And yeah, I think we have one question in the Q&A that we can respond in the meantime.
So Anita is the expert on this data set and knows a lot more about the particular parameters than I do for this data set.
Anita, do you answer the question?
Yeah, I just answered in the chat, but
Okay.
just to summarize what I said.
Okay.
As a specific example in this data set, the noisiest antennas are the ones on the longest baselines. And if you downweight them, then what you'll essentially be doing is increasing your synthesized beam, and you will not be picking up the detail of the source structure so well. So your model will actually be lacking in the detail that's needed to try and correct those antennas in the next round of self-calibration. So I would use cal weight equals true at the end when I finished, or at least I would experiment with it. But it's not a hard and fast rule. We can discuss it some more if there's time, but that's the short answer.
Thanks, Anita.
Oh yeah, that's a good question that's up now. What is the minimum brightness of your source needed to do the most basic self-cal?
Basically, you can approach it in several ways. We're actually going to be talking about this in the final part. And you can work it out analytically. And this relates to how long a solution interval you need. But generally speaking, you would start by saying, okay, probably the longest sensible solution interval would be the entire length of a single scan. You can then work out, bearing in mind that gain cal decomposes the solutions per antenna, you can work out what the signal to noise per antenna would be for your actual observed signal to noise with the whole image using all the antennas. And so you can then say, okay, I would have a signal to noise of 10 per antenna, all being well, so that should be fine. Or, well, I've only got a signal to noise of 3 per antenna. That might work, but what I probably want to do is, average my spectral windows, more average polarizations. So there's no hard and fast answer. The other answer is to do it empirically, which is to plot your data phase against time. Just go through baseline by baseline, or just look at baselines to the reference antenna. Just look at a few baselines if you've got zillions of baselines, and try a different amounts of averaging in the plot, because what you want to do is to see, can you see some kind of coherent pattern from averaging interval to averaging interval? And if you can, then probably that's going to be okay for self-calibration. If you can't, it might just be a very complex source, but it probably means that there isn't enough signal to noise for self-calibration. But we will be going into this, how you actually derive the expressions later.
I'd like to add something on to that. And Anita, please correct me if I say something incorrect, but another way to empirically do it is to focus on the dynamic range that you might have in your image, in a test image that you would make. So I've had more experience with VLA data, and I was told, like around 100, a few hundred, if you just make a test image and look at your peak versus your noise. I think with ALMA, with the full array, it's less. We'll have a few numbers for ALMA data in particular, but Another empirical way to look at this is your dynamic range of an image that you would preliminarily make. So.
Yeah. Basically, yeah. I mean, the thing which we'll explain later is that, contrary to what you might think, the more antennas there are in your array, the higher signal to noise you need. Because if you think about it, it's actually going to sort of be decomposed further because you've got more antennas. So in other words, for sort of, VLBI with 5 antennas, you'd probably try self-calibration if your image signal to noise was 10. But for ALMA with 45 antennas, then a couple of hundred is probably where it's worth starting, although you've got nothing to lose by trial and error.
Yeah, that's another thing of just also it's self-calibration is an art too. So trying it to see if it helps with the dynamic range of your, but yes, of course, using caution of there is still some sort of min signal to noise that you could have that it would help. Okay, we've got another question.
And this is about the selection of the channels that you want to use as calibrator, and when those solutions are applied to the entire data set, right? So at the beginning, you start self-calibrating only with those, for example, the continuum, and then you do a run or a couple of runs on the continuum, self-calibrating the continuum, you get a better model, and then when you are happy with it, you apply that to the rest of the visibilities. Is it going to be applied to the ones that were flagged before? I'm not sure, I don't think so. Only if the CalWT parameter is true. Is that correct?
Can I just ask Thomas a question? Do you mean, because there is one sort of style of self-calibration where rather than just doing a continuum channel selection like we did, you actually flag the line channels. And if you do that, then you need to unflag them before you run apply cal. Yeah, but basically, if you flag channels purely because they're line channels, not because they're actually wrong, then you need to unflag them. And I think, yeah, I'm not quite sure where the question was coming from.
It's stomach, but yeah, it's actually a good point, Anita. Yeah, if you flag them because you don't want to use them for the model, then you need to unflag them. Yeah, sure.
So it seems, yeah, I'm not sure. It seems like we're not quite sure if it actually applies the solution to the flag channels or not, but.
Yeah, no, I actually, my understanding is that if channels are flagged, then the calibration, I think you would have to unflag them before you run apply cal
to have it actually applied.
That's why we just make a channel selection rather than flagging channels. And if I were going to flag channels, I would actually make 2 copies of the data set, because what you kind of, if the data set's small enough, I would make a continuum data set and a line data set separately. And then I would run apply cal from the calibration tables I derived using the continuum. I would apply those to the line data set to the equivalent spectral windows.
Yeah, there is the follow-up question on this attendee. Yeah. Do you want to respond it? In 1 minute, we will continue, and then we will also have the advanced lecture where we will go more in depth in all the, well, Anita will go more in depth in the details.
I think if you have an incredibly bright point and all you want to do is to measure its position, for example, then there's no point in doing self-calibration because you can't improve the astrometry. by calibration. And equally, there is an upper limit to how, I mean, you can do quite a few rounds of this antenna-based calibration, but if you have a signal to noise of tens of thousands, then you start getting affected by baseline dependent errors. But yeah, I mean, you can do self-calibration for those, but you need to be really confident you know what you're doing. Similarly, if you find you need to do bandpass self-calibration. Kazi and I have both had experience with planets where, yes, I mean, that if you had a specific example, we could maybe discuss it later, because there is a huge difference between doing self-calibration on a nice, well-behaved point like Quasar, for example, and some monster like Venus, which gives me nightmares.
Okay, thanks, Anita. I think we should keep going to make sure we have enough time at the rest of the hour. So we left you this break to think about what the solution interval you would apply for the next cycle of self-calibration. And we gave you some hints. Now I'm just going to quickly explain what the tutors decided to do, which we decided to apply a 60-second solution interval. And we did so you can check in the script, the step 11, in which we calculate a new table by applying the previous inf table on the fly. So this is how you would do it. Yeah, we use a spectral window. We use the continuum channels to calculate solutions. And the spectral window map means that we are going to apply solutions from a spectral window 0 to a spectral window 0, and solutions from a spectral window 1 to a spectral window 1. And there is more information on the additional slides about this spectral window map parameter. Then in step 12, to be consistent with the way we calculated the 60-second table, we apply the two tables consecutively. And we also do it consistently with the spectral window and the spectral window mapping. And finally, in step 13, we do our last image of this tutorial. And we, as you can see, have a very significant improvement of the signal to noise. So after looking into the gain cal tables and how many solutions are flagged and how well are we tracing the variations, we decided to apply 60-second interval, but we think any solution around 40, 80 seconds, it's a good choice because it keeps that balance, as I said. And in the advance, Emily will explain a bit more how to support your decision based on the signal to noise of the solutions. Now, for completeness, I show you here the gain table for the 60 seconds. As you can see, we have about 5 points per scan where we are tracing the phases. And well, this is the final image. This was the first initial image which Emily started the tutorial. And this is the image that we obtained after the second cycle of self-calibration. And to wrap up, I just wanted to show you, following up on what Emily showed, what is the impact on the visibilities of this exercise. So here, well, if you are not familiar working with visibilities, do not worry. You just remember that the phases, the phase visibilities carry information on the shape of the source and the location of the source. And unless a source is really changing shape and location during the observation, we would expect that the source looks the same during the full run. And this is actually what we are forcing with self-calibration. So with self-calibration, we are forcing the source to be the same along all those scans. So here, remember in the first inf loop, we are only applying 1 point per scan. And that's the impact of applying that in the visibilities. As Emily mentioned, all these red points become the blue points that are more equalized at the same level. And then in the second round of self-calibration, we applied yet another 60-second solution interval on top of the inf. And what you can see is that now the points here are more clustered together and they resemble like a coherent stream. So I will just look this quickly and you can see what is the difference. And now that you all feel the power of self-calibration, I'm sure you would like to keep doing cycles of self-cal ad infinitum. But yeah, a very legitimate question is when I should stop doing self-cal. I will just leave this slide for information in the, here. I will not go into it because this is the very best way to give the floor to Anita for the advanced part.
Okay, so thanks very much for doing the interesting bit. I'm afraid this is the more boring bit, but I'm where you're listening to us just talking, but I'm sure that you're actually still doing the interesting part and doing the hands-on stuff as well. And I have to say, I was also quite embarrassed when I saw the list of people attending, as at least some of you know more about this than I do. So hopefully there'll be time for an interesting discussion. And this is the list, an index list of what we'll be touching on very briefly. If you want a proper derivation of these topics, then you should look at something like Thompson, Rall and Swenson, the VLA summer school proceedings and so on. But we'll try and show that there is actually some sort of real reason. The numbers and so on, which we've been entering, aren't just plucked out of the air. So the first one is the question of choosing a solution interval. And as I mentioned, what typically you would do is that you would look at the data, the visibility data, and you would also look at an initial image and measure the signal to noise in that image. So you can say that ideally your signal to noise is given by the system temperature divided by the square root of the number of baselines, the frequency interval that's gone into that image, and the total total integration time that's gone into that image, the actual time on source. Of course, in your initial image, the noise is going to be quite a lot higher and the signal is probably going to be lower. But this will give you a sort of ultimate value. And because each antenna has n-1 baselines, and you've also got extra degrees of freedom due to the origin of phase and the reference antenna. So the noise per antenna is given by the noise per baseline divided by n-3, all square rooted. So it's essentially it's roughly n-3 higher, a factor of n-3 higher. And so then you can do some sums. I'm not going to talk through the derivation, but basically you've also got to bear in mind that you want to solve in a single, maybe a 5-minute scan interval, but you've actually been observing, say, 2 hours or something. So you need to calculate the signal to noise in the shorter time interval. And similarly, if you're going to derive independent solutions for each polarization and each spectral window, then the required signal to noise has to take that into account as well. So you end up with an expression for the noise for a single antenna, for a single spectral window and a single polarization. And then you can invert that to say, okay, what is your minimum solution interval? And so it's essentially it's the expression in the box here for the various factors on the top, the number of polarizations, number of spectral windows, number of antenna, divided by the square of the 3 sigma signal to noise, assuming that you're saying, okay, I want a minimum of 3 sigma RMS on each antenna in each interval. And as I've already mentioned, initially you're not going to have as good a signal to noise as you're going to eventually end up with. And we've also already covered the question of weights. So initially you want to use a larger than ideal solution interval. The reason for choosing 3 sigma is pretty arbitrary. In an image, you could say that if you have 1000 pixels of, actually if you have 512 pixels on a side in an image, then there's going to be a few tens of individual pixels that purely by chance are outside the 3 sigma distribution of noise. But there isn't obviously a linear translation between noise in the Fourier plane and noise in the image plane. But roughly speaking, the 3 sigma criteria usually gives tolerable results. If you had a really poor model for the first few rounds of self-calibration, you might want to have a much lower cutoff, if 1.5 or even 1 signal to noise, simply if the problem is not that the data are inherently bad, but that, say, your phase reference source was a really long way away from your target or something like that. But hopefully by the time you've done a few rounds of self-calibration, you won't be failing very many solutions with a signal to noise of 3. And if you've got the time, it's often worth checking if it's always the same antenna, the same interval that's failing a solution, and maybe there's a bad data that should be flagged. So Emily is now going to go into more detail about the solution interval. So I'm just going to stop sharing my screen if I can find where to do that.
So Anita just went over how to analytically determine a solution interval. I'm going to speak about a more empirical and just very brute force and practical way to do this. And so in the script, we gave you some lines of code that allowed you to explore different solution intervals. So a good way to go about exploring solution intervals is to look at 1, 2, 3, 4, 5 times int, or also to do 2 to the n, so 2, 4, 8, 16 times the interval time. You can also look at inf divided by 2, inf divided by 4. And what we can do then is look at the signal to noise distribution of these solution intervals. So again, I just wanted to show you what this looks like. Panelists, is this Zoom box inhibiting any part of the presentation? Can you see?
I see. Well, yeah.
I only see the slide.
Okay,
Yeah,
excellent.
yes.
Okay, then I won't care about
Yes.
it. Thanks. Thank you. Okay, so this was this is showing the solutions on the int level. So again, just to remind you about that, so you can see the variations. It's always I have learned to start this way just to look at the solutions. So this is the signal to noise distribution of a 10-second solution interval. And this is for the gain tables, not the image. This is really quite interesting. So you can see some peaks, and then also here, which we'll talk about a bit more. But then we can look at solution intervals of 20 seconds, 40 seconds. You can see we're still sampling this variation, and 80 seconds, 160 seconds, and then inf. And here is the signal to noise distribution of the solution interval of inf. And there are functions and lines of code in the script that you've been given for you to reproduce these plots. But here is what this looks like for various solution intervals for 10, 20, 40, 80, 160 seconds. And I wanted to point out a few things. So first of all, this peak here is the failed solutions for each gain table. So we want to try to minimize the number of failed solutions. So you can see that decreases with the solution as the solution interval increases. You'll see that there is this movement of this first peak of the signal to noise distribution. It moves to higher signal noise as you go to higher and higher solution intervals. And then you can also look at, this is an area of interest if you're using this way to choose an optimal solution interval. It is, this is the area in which it's close to where the solutions will be flagged, in that the default is a signal to noise ratio of 3. So you can see as you go to higher solutions intervals, you get less of these solutions that will end up being flagged. So here is just to take out a few of them to get rid of a little bit of the chaos. So you have a decrease in failed solutions as you go to increasing solution intervals. You have this increase of signal to noise generally as you go to higher solution intervals. And you can see down here that there will be less solutions that are flagged. And you can actually be very picky and actually get some qualitative numbers of how many solutions will be flagged, et cetera, for these different intervals. But we want to balance flagging solutions in this area while also capturing the variations of the phases. And so again, yes, we have this movement of the signal to noise peak to higher signal to noise. So as I mentioned, you want the shortest solution interval that balances both sampling those variations in the solution while also flagging the least amount of solutions. So we'll want to be in the middle of those plots. So for us, that really seems to be between 40 to 80 seconds, where you have less failed solutions between 40 to 80 than the 10, 20. You also have higher solution, higher signal to noise distribution, a higher mean. And you can see that that's where we have a large decrease in the number of these solutions that will be flagged. So through this analysis, it could be anywhere between 40 to 80. It is an art, so it's not an exact science. So we did choose 60, but probably 40 or 80 would also have been fine. So we got inspiration from this from a CASA guide that Josh Marvel and I wrote on self-calibrating a VLA data set. And he came up with this analysis, the way to show these solution, the signal to noise distribution of the solution intervals. So just a quick word that there are different ways of applying the solution intervals, different sort of schools of thought. So you could quickly find this optimal solution interval using these signal to noise plots and just continue to apply that through your rounds of self-calibration. You can also do something similar to what we did in the tutorial, where you start with inf to apply those scalar corrections and then decrease the solution interval to continue to capture the structure of the variations in the phases. And continue down to a smaller solution interval. So again, it's an art, not an exact science. And you may have problems with the signal to noise that you have in your gain tables, and there are ways that you can increase your signal to noise. You can combine spectral windows if the gain solutions are quite simple or similar. And you do that using combined spectral window. And then apply cal, you need to give it a spectral window map to tell it how to apply. So if you combine all of them, you say 0 for the number of spectral windows to use that for all of them. But you might have the case where there are some spectral windows that are normal to broad, where others are narrow. In this case, you want to apply maybe the good solutions from the broad ones to the more narrow ones, or to all of them. You do need to check if you have offsets between the spectral windows by plotting these solutions to make sure that they're all pretty similar. And if they're not, talk to a colleague that can help you figure out how to do that. You can also combine polarizations using gain type equals T if the solutions are quite similar again. So these two ways will help you increase the signal to noise in your gain tables, and then allow you to flag less solutions. And now I will hand it back over to Anita.
Okay, so thanks, Emily. And just to carry on, these are a few points about what to do if you've got, for example, quite inhomogeneous data. And this is actually taken from a ACA example where spectral window 18 was a full nearly 2 gigahertz wide, and whereas spectral window 32 is a very narrow, high resolution spectral window. And there are two ways of coping with this. And the way that I think that the pipeline quite often does it is simply to average all spectral windows together, which usually works, although sometimes the narrow spectral window is actually so narrow that it adds noise in that averaging. And the other alternative is to derive the solutions for the broad spectral windows with the good signal to noise, talking about deriving continuum solutions, and then apply those to all spectral windows. And in this case, it's fairly obvious because spectral window 18 actually overlaps spectral window 32. But as I think there is a supplementary slide explaining, sometimes you have to look at the list in list obs quite carefully to figure out which spectral windows between the wide and the narrow correspond to each other. And this is also, because I've tried to make some simplified plots, in reality, you might have some channels that were being excluded because they had line emission in them. But here I'm just looking at assuming that they're all the channels are being calibrated. And usually, if you're in this situation, you would use the bandpass calibrator as what Alma refers to as a diff gain cal. And what you would do is to make one solution averaging all times for each spectral window using a source which is bright enough to give good solutions. And then apply that every time you derive solutions thereafter. And what that does is that it removes the difference between spectral windows. So it doesn't actually provide a good solution in the imaging sense, applying the bandpass calibrator solutions to the target. But what it does is that it means that if there's an offset between polarizations, then it will be removed by the application of a single solution. And usually if phase referencing has worked properly, the phase reference source also aligns everything. So this is something that you may not need to worry about, but if you are going to be transferring solutions between spectral windows or between data sets in some other way, then you need to check that your spectral windows are aligned. In other words, that when you plot, you don't see some big offset like you see in the panel B here. And if you apply a correction for those offsets, you can even use the target itself to derive the offsets, because if you're averaging across all times and all channels, then you're still maybe getting enough signal to noise to do this. And basically your solutions in the end should have all the polarizations lined up. And even if the different antennas obviously have different slopes, because you're decomposing the baseline you're plotting from the data into the individual antennas, the slope should be about 0. There shouldn't be big offsets. And this is again something which you will come across, for example, if you are observing a spectral scan, so that you have data taken at everything from, for example, 220 gigahertz up to 270 gigahertz. And in those situations, the rate of change of phase with frequency is a function of the frequency. And although within the typical sort of 10 to 20 gigahertz of the single Alma band, and certainly above band 3, the difference that makes is less than 5 degrees. So it's usually less than the best phase error you could hope for. When you're transferring over larger intervals, you need to use this PD suffix in your interpolation parameter in apply-cal, so that what that does is scale your solutions by frequency so that they become appropriate to apply to a very different frequency, typically if it's more than 20% different. And this is also what's used in band-to-band phase referencing, where you can see that the phases change quite drastically if you look at the solutions in the top panel between bands 3 and band 7. But if you scale the band 3 corrections by the ratio of the band frequencies, then you can apply them properly. There's actually a lot more complications in band-to-band phase referencing, and you should see the paper by Yoshiasaki and Luke Maud on that if you do get band-to-band data, which is likely to come through in the next cycle, I think. So something else which we wanted to touch on was what you can't cure with self-calibration. Although I have to say that some people, including my great mentor, Ed Fomelant, used to use self-calibration kind of like using a hammer to bang in a screw in desperation, because self-calibration will show up where you've got that data. It will show up many of these faults, and you can use cal flag equals true to get rid of it. But it's not actually solving the problems, it's just brushing them under the carpet. And sometimes that's all you can do. It's a perfectly legitimate thing to do if you've tried everything else. So if your target is really faint, then you can't self-calibrate. There are exceptional circumstances. Maybe you have one antenna that is, the flux scale has just gone completely wrong, and you might try averaging all your times and just bring that one antenna under control. But usually, if your signal to noise is too faint, you're only going to make things worse. At the opposite extreme, if you've already reached the thermal noise, it might be worth trying one round of phase-only self-calibration, because you can have a small amount of smearing of flux without having ruined the noise. But usually, you're not going to get below the thermal noise, that's for sure. And if data are completely bad, like the telescope wasn't actually pointing at the source, it's completely incoherent, the phase has no structure to it, however much you average, however much you maybe try and put in the, in plot MS, you can put in a shift to make what you think is your source at the phase center. If it's noise, you can't save it. We've already mentioned basket weaving and other symptoms of missing spacings, and those you can mitigate with imaging by suitable weighting and calibrating the longest baselines properly will improve the image. But if you've got missing spacings, the only thing you can do to improve the image ultimately is put in more data. Similarly, if your target is variable, then like you have a flare star or a very, very compact AGN, which is variable, then you have to do something like subtracting out the variable data. And that's the sort of thing that could be discussed more if you run up against that particular problem. Antenna position errors. If you have a fairly simple structure source at the phase center, then you can solve that. Self-calibration will help to reduce the effects of that. But the problem is that basically that the reason why this affects images quite badly is because it affects the accuracy of transfer of solutions from the phase reference source, because all the delay corrections are slightly wrong. And probably, particularly if you have a very complex source or a source where the brightest emission is significantly offset from the phase center, you'll have trouble getting a proper enough model to self-calibrate with. If you happen to have a good model from a different session or something, then you might have some luck with that, but it's very difficult to cure those errors. And similarly with pointing errors, you can mitigate the effects, but probably your amplitude scale will never be quite right. And if it's an extended source, that you can't cure the problems completely. We've already mentioned baseline dependent errors. And also, if you have bandpass or delay errors, then I've never successfully done bandpass self-calibration. I know one person who I think has, maybe two people, with really bright sources where they've known the spectral index of their source very, very well from previous work. But it's really, you want to go back and try and get the bandpass right using the bandpass calibrator. The bandpass errors are mainly instrumental. So if you have a number of executions, then you might be able to use the bandpass calibration from a few hours or even a day or two's difference, as long as all the antennas are the same. When do you stop? So basically you stop when nothing gets better. With phase, then keep going, keep shortening the solution interval, as long as the diagnostics that we've been discussed suggest that it's realistic to do that, or as long as you see the model for your image improving. There's no, if you have a point source, then there's no point just carrying on doing self-calibration with the same solution interval and the same point, and nothing's going to change. And usually we get the phase solutions as good as possible first, because the causes of amplitude errors change more slowly, but you need more signal to noise for amplitude self-calibration. And you should always check as well. And for example, with the V/CMA data, when I was self-calibrating on the Mesa in an individual channel where I had a very bright point source, I would stop after each round of self-cal and also image one channel where there was an extended line to make sure that I hadn't inadvertently forced all the data to look like a point, because it is possible to do that if you have long baselines that are very well constrained narrow channels. For amplitude self-calibration, usually with ALMA data, if the source is bright enough to self-calibrate, then it's bright enough that you will need to start by making an image with the spectral index term as well, make the TT0 and TT1 images with deconvolve or MTMFS. And you want to be careful that once you've got the phase solutions right, then you can clean down. So you want to make sure all that flux is in the model for amplitude self-calibration. And as the amplitude errors change more slowly, I would probably go back to using a full scan length for the first round of amplitude self-calibration, and then keep going again until there is no further improvement. If you see the flux decreasing, even if the signal to noise has got better, that's also a signal that something is wrong. Your model hasn't got all the flux in it, so you should go back and redo it. You need to include all the significant sources in the field of view, even if they're not what you're interested in, as you do to get a good image anyway. And if your signal to noise has increased a lot, then it may be that some bad data which was hidden before in the sort of phase errors may appear. So you may need to do more flagging. If you've got a mosaic, then usually you just want to select the brightest field, because that's the one with the source that's going to give you good signal to noise. And you essentially treat that as if it was a phase reference and apply its solutions to all the fields. For polarization, if you use gain type equals T in gain cal, that will average X and Y, which means that the solutions will be good for the average and you won't destroy the actual intrinsic offsets between X and Y, which will give you your target polarization. But you do have to be quite careful about that. And you may have to do a sort of hallucinative thing of doing some polarization calibration, then doing some more self-calibration, then redoing the polarization calibration. For extended objects, you can use multi-scale clean, and that the model that produces what works perfectly well in self-calibration. I've already mentioned amplitude self-calibration. And if you want, this gives you a quite so simple way to analytically check that you do have enough signal to noise to be worth solving for the spectral slope as well as the total intensity. And of course, if you have a very bright source, then you might want to go to more than 2 terms. So calibrating on the line or the continuum, then something which I actually learned since I first did these VY-CMA data is that if possible, it's better to start with calibrating on the continuum, because you can quite often have small amplitude scaling errors between different spectral windows, and self-calibrating on using all the spectral windows to make a continuum image, excluding the line, of course, or the line-free continuum, will get rid of any small offsets in the scale between spectral windows. You want to make sure that you pick the line that's got the brightest peak, as you see in the right-hand image, which may not necessarily be the brightest line in the spectrum, because a lot of extended emission will add up to something which looks bright in the visibilities. But actually, you would have a much harder job getting a nice model from the ring on the left than the point on the right. And if you're combining executions for spectral line self-calibration, then before you do any self-calibration at all, or before you select your channels, you want to run MS transform with the parameter to regrid the MS into constant velocity in the target frame. Because as you can see, if we're observing from Earth, then as the Earth is moving, the observed frequency will change, but you can then transform that to constant velocity in the target frame, and that will shift the channel numbering quite significantly sometimes. And it means you get much better signal to noise because you're piling all the good emission up in a single peak. These particular data are fairly pathological in that we were observing in the waterline. So this is a particular reason why the solutions from the water maser may actually hit a part of the atmosphere that has that has dispersive as well as non-dispersive delays. But usually you're quite safe applying calibration from the brightest line to all the channels. Yeah. Okay. So something which we noticed with the VY-CMA data, and I've also noticed in other instances, a very common instance actually is this one, which is that the target data, the last scan is not properly bracketed by the phase reference source. And so here, you see, let me just get this more central. I'm trying to make it a bit bigger for you. So here you see that the last scan was completely missing on the phase reference source, and the target data, after applying the corrections, the last scan is very noisy. And actually the scan before that is quite noisy because the phase reference was setting. And so when we made the first image number 1 here, applying the phase reference solutions using all the target data, it had this really weird sort of cloverleaf structure, or like Mickey Mouse lying on his side. And it turned out that that was because of the inclusion of the uncalibrated data. So rather than just completely flagging the last scans, we made an image just from the first 2 scans, which produced a very nice image, image number 2. And I can see what's happened is for some reason, Google Slides has destroyed my image number 3. I should have been like Emily and done it from a PDF. Sorry about this. Anyway, you can take my word from it that having first of all just used the first 2 scans, we made a nice model. We then went back and calibrated using all the scans and got a nice self-calibrated image for the whole thing. Similarly with the VY-CMA data, one of the antennas had a few scans where for some reason the rate of change of phase with time went crazy. So in the script that you're working on, initially we flagged that antenna completely. But what you can do is then make a nice model, include that antenna so make a nice model excluding the antenna, and then in GainCal unflag it and you can, as long as you use a short enough solution interval that you're sampling that slope, you can see that, you know, the phase is not noisy, there's just something strange happened. So as long as you're sampling the slope properly, you can correct for that slope and restore that antenna, the data from that antenna to include in future rounds of calibration. Okay, so I'll now move on to my next slide. The analytic basis for the source of error, or how you can figure out what the effects on your image are going to be if you have some level of phase error, a residual phase error. So in this example, you have phase reference scans alternating with target scans. I've only shown the phase reference scans here. And the overall slope of the phase is about 180 degrees in 20 minutes, or 36 degrees in each phase ref target cycle. And you also have to take into account not just the difference in time, but also the separation on the sky. And the separation on the sky here was 2 degrees. And you can use the fact that the Earth's rotation is measured essentially in minutes of right ascension to get an equivalence between the effects that you see as the phase changes with time and the effects of the difference in position on the sky. And taking into account the cos-dec term, 2 degrees is equivalent to about 7.5 minutes of time. And so you can say that we've got, roughly speaking, 65 degrees of phase change, phase error due to the sky separation, and 36 degrees of potential phase error due to the difference in time. But because we're interpolating linearly between scans, the worst of that error will only be half that. And this turns out that you're going to have an average error of about 37 degrees. It's interpolated across target scans. And in addition to that, there is a small scale jitter. So if you did self-calibration on the time interval of a full scan, you would still have left about the sort of 10 degrees in 30 seconds of jitter. And from the basic expression for a complex visibility, V equals E to the I phi, where V naught is the actual visibility amplitude and phi is the phase, then if you take the expectation value, then you can say that the visibility that you see is going to be reduced by a factor equivalent to E to the half the square of the phase RMS. Essentially, a 10-degree phase error produces a 2% reduction in amplitude. Dynamic range is another issue. And if your phase reference source, for example, has a dynamic range of 200 to 1, essentially, you're never going to get a target dynamic range better than that without self-calibration. There is an expression which is derived in synthesis imaging, chapter the 1999 BLA Summer School Handbook, which I have to say, it's available online for free. It's absolutely invaluable. So roughly speaking, the dynamic range is for a large number of antennas and a relatively small phase error, n over the phase error, for each period during which the atmosphere is the same. And so if you have n periods where the atmosphere changes, you know, in other words, the time it takes for a particular disturbance to pass over your array, then it's the total dynamic range is increased in proportion to the square root of that. And there's a similar expression derived for amplitude errors. And for these data, you can work out that 2 hours on target, 2 hours duration of observations, 2.7 kilometers baseline, typically 5 kilometers an hour wind above the Alma site, or you can look it up. Actually, there's a weather monitor you can go back and get the information from. And this says that the maximum dynamic range due to phase errors would be about 54, and the maximum dynamic range due to amplitude errors would be about 280. So this tells you, first of all, that phase errors are worse than amplitude errors. And secondly, that this expression is actually valid, because if you remember back to the dynamic range that you got in your first image, it was about 55. So yes, Rick Perley was right, always. So this is a few other things about the self-calibration on a compact peak, just going through what you've actually done. And just to mention another thing which has already been touched on, phase errors essentially represent the sign term in the expression for complex visibilities. And that's why phase errors tend to be anti-symmetric. You get a negative on one side, balanced by a positive on another, whereas amplitude errors represent the cosine term and tend to be more symmetric. And as we're increasing our dynamic range with the self-calibration, we actually end up with a dynamic range, ideally of about 840. You might get to 1,000 if you do it very carefully. Whereas if we use the phase ref only, we wouldn't get beyond just over 100. Okay, so there are two ways that you can build up the self-calibration corrections. And the way that we've been doing it is to always work on the same measurement set, but to accumulate gain tables. So the first time we just applied gain table phase 0 and in apply cal. The second time we applied that gain table in gain cal, we derived a new gain table P1, which just contained the incremental additive solutions, much smaller solutions. We applied 2 gain tables in apply cal. Then if you carry on, you would apply those 2 gain tables in gain cal, and you'd have 3 gain tables in apply cal, and so on as you're carrying on. And I find that's easier to, if you want to go backwards and redo a step, then every time you have to remember that imaging will normally work off the corrected data column, but gain cal always works on the pure data column. So it'll only take what's in the data column plus any gain tables you give it. But what you can do is split out your corrected column so it forms the data column of a new measurement set. And I think some people find it simpler to do that at every stage, so that you only ever have to apply one gain table in apply cal, and you don't have to worry in gain cal. On the other hand, of course, that increases your data volume. It doubles it at every step. But as long as you're consistent, the crucial thing is not to sort of try and do both. You need to be consistent. Why do we do phase first, then amplitude? Well, mainly because the phase solutions tend to produce the biggest improvements, particularly with ALMA data. And occasionally, as I've said, there are situations, particularly with VLBI, where you might do something different. But talking about ALMA data, the phase solutions tend to produce the biggest improvement because the phase change in the atmosphere is what's hardest to correct for, what changes most rapidly. And you can't get a good amplitude model unless you've got the phase well corrected first. A slightly more analytic approach is to look at the closure relations, although I need to stress that gain cal does not actually use the closure phase relations. It uses a different method to solve, but the principle is the same. And essentially, because phase is the additive term in the complex visibility, you can get a good, you can get rid of phase errors by adding up the phases, including errors, across a set of 3 baselines. The errors will cancel out. Whereas because amplitude is the multiplicative term, you need 4 antennas. You need more baselines in order to be able to divide out the amplitude errors. Okay, and so what influences your final image accuracy? For astrometry, there isn't time to go through this in detail, but shut me up if you think I ought to stop, but I will just say basically, again, you can look this up, but antenna positions are the most crucial thing. ALMA now knows its antenna positions pretty well, as long as you've made sure you've applied any position corrections that might be derived even up to a week or two after antenna moves. But for data prior to about cycle 4 or 5, that might be a problem. Phase reference position accuracy, again, usually very good. If you're worried about it, particularly for sources in the far south, then you can even ask to perhaps have your phase calibrated position refined. And then there's what we've been discussing, which is the phase correction accuracy. And then, of course, the target signal to noise and the resolution. But in terms of absolute astrometry, you cannot improve that by self-calibration. The model you put in is the basis for what you get out. So if you want to measure the absolute position, then you should always do it before any self-calibration. And similarly for your flux scale, you should measure your flux scale usually before you've done any amplitude self-calibration, unless, as I've said, there is some huge problem with the amplitude calibration. So your most accurate flux will probably be after you've applied all your after all your phase self-calibration solutions, but before amplitude self-calibration. So what to do if you've tried self-calibration and blah? Well, first of all, have a look at the phase reference. I mean, really, you should do this first, but of course people don't, they just dive in. First of all, have a look at the phase reference image or whatever you've got delivered. Did that all look okay? Is there anything in your logs that should ring a warning bell? Make sure that you've been cleaning properly. Have a look in PlotMS and make sure that you haven't accidentally flagged all your data or something. It's amazing how easy it is to do this sort of thing. Check on the basis of how much data you've actually got, what RMS you're expecting. Make sure you didn't make some kind of bookkeeping mistake in applying the self-calibration. If your first image looked okay and the signal to noise was really high, and then calibration, you apply the solutions and you get a complete mess. Maybe you need to do some more channel averaging, or maybe you need to taper the beam. Maybe if you've got very long baselines, you're being dominated by errors on a few long baselines. Have you missed emission off the edge of the field of view, or are there a lot of missing spacings? The question of, do you need to solve for the spectral index, particularly if you have even with a single data set in band 3? And if you've got very extended emission, then using multi-scale will help. So this is a selection of errors, some of them exaggerated, some of them from real data. And I don't know whether people want to sort of try and say if they can spot what each of these is, or whether I should just go to the solutions. What does anybody want to have a go at saying what they think some of these might be? So I will just go on to the next slide. Yeah. So basically, I'll just explain this very briefly, and this is actually the end of the presentation. You'll be very glad to know. So the stripiness might be bad data, but it could also be a very far off confusing source. But usually, if the stripes are completely parallel, then it's bad data. And in theory, you can figure out whether it's on a long baseline or a short baseline. If the stripes are very close together, then it's an antenna on a long baseline that's giving the bad data, and vice versa. And as I've mentioned earlier, symmetric errors, as in the image number 2, are probably amplitude errors. Phase errors are anti-symmetric. Number 4, it might just be that you haven't cleaned enough, or it might be that you've got missing spacings, and so you have this sort of negative bowl around your target. And the last one, which is quite subtle, this is what we were talking about as basket weaving, but actually there's another possibility for something like that is in continuum, if there's delay errors. In other words, if there's some kind of mismatch in phase between channels. And the way to test for that is that if you use some kind of more tapered beam, or maybe, you know, try robust equals 1 or something. If you were using robust equals 0, try a higher value of robust. And if it's due to missing intermediate spacings, then that will make a dramatic improvement usually. If it's due to bandpass or delay errors, then it's not going to make any difference what you do with robust. You need to fix the errors. So just finally, thank you all very much for bearing with us. And I hope that, well, we learned an enormous amount preparing this work, actually. So I hope that everybody here has learned something. Thank you.
Yes, I will say an applause. Yeah, thanks, Anita, for sharing all your knowledge with us.